Hey guys, this is Academic Challenge Pre-Calculus lesson number 10.7. So we're going to talk a little bit about parametric equations, and these are going to be very different than anything you've been accustomed to, but I think once you learn them, you'll actually kind of really like what's going on. So we have a curve, and it's represented, we have a representation for x and y in terms of t. So how do we do this? We go ahead and we choose values of t within that domain we're given. Okay, so this sets up a nice little chart for us to see. So all these values of t, we plug them into our x expression, which is that 1/2 t. We plug them into our y expression, which is the t squared minus 3. And as we do that, we get x, y points. So, whoops, let's go back. So notice how we get these points. We can plot these points, and we get something that truly looks like a parabola. So that's how you would go about graphing it if it was in parametric form. But these are also convertible, so we can go from parametric form into our standard Cartesian form. So we have, or we call it rectangular equations to go back. So when you have your parametric, so here's the representation for x, here's the representation for y. So this is kind of like what we were doing. We're going to take this expression for x. So we solve, first thing you do is solve one of them in terms of t. And in this case, it's easier to solve for x in terms of, or solve for t in terms of x. So we have 2x equals t. We plug that in for t. And now we have an expression for y in terms of x. When we're all done, we're done. So this is our expression, and this is showing us that parabola that you just saw in the previous picture. The only thing you have to worry about is the limits at the end. So if t is between -3 and +3, we have to plug in, okay, well, what was t in terms of x? So t in terms of x was the 2x, so we do that, divide by 2, so that means x has to be between -3/2 and -3/2 and positive. And you can see that in this picture, that that's where the graph actually stops. The other thing you would do is represent it with like an arrow, which is not in this picture. But parametric equations are always represented with arrows because they're kind of related to real-world problems. So just a little bit of terminology. Y equals g of t is a plane curve. F of t and y equals g of t. Those are called your parametric equations. And t is called the parameter. So here's another one. X equals t squared, y equals t minus 1. In this case, we already have x is equal to t squared, so that means t equals plus or minus x. So when we plug that in to here for t, we have y equals square root of plus or minus x minus 1. So it's represented by, some of these don't come out. Remember, we're not limited to functions now. So we have that, and then we just talk about our parameters with respect to x, and if we were to square x, then we would get between 1 and +16. So what about cosines and sines? So these can be a little tricky too, but remember the Pythagorean identity that we learned. So remember, cosine squared plus sine squared equals 1, which is great. So we look at this, and this might be a little confusing. I wish I detailed it out a little more. So if x equals cosine and y equals sine, all we have to do is square x and square y. So if we square x and square y, we have cosine squared plus sine squared equals 1. But what is that really? It's just x squared plus y squared. So it's a little trivial. Hopefully you understand that. And again, if you need me to draw any of these out, I can. We can just do it in the Zoom meeting. So just make sure you let me know if you struggle. Now this one's a little different, but same concept. We're going to divide this through by 5 and divide this one through by 3. And you can see, because if x equals 5 cosine t, and we get this in the form of x over 5 equals cosine, y over 3 equals sine, then we set it up because that cosine squared plus sine squared. So here's cosine, here's sine, we square them both and add them, and that equals 1. And we end up with an ellipse. So this is just the equation of an ellipse then. Okay, so then we have the type of problem where we're actually going to find 3 sets of parametric equations. These are really, really easy. Don't make them too hard. So if we get to pick our values of t. So let t equal x. So if t equals x, we just plug it in, and it's literally the same thing just with a t in it. We could say t equals t plus 1. If we plug that in, we get this. So you're just literally plugging it in for x, and we get that. And if x equals t squared, we plug t squared in for x, and you're done. So if it just, especially if you run into a homework or a test question where it says find 3 sets, but it doesn't tell you what t or what x has to be or what t has to be, you just do it this way, okay? So a lot of these equations are very related to physics. So you'll see a lot of physics problems. So looking at this, baseball is thrown from a height, 6 feet, with an initial speed of 100 feet per second. We have a lot of different solutions going on here. So let's work the parts. So first thing we want to do is find parametric equations that give the position of the ball at time t. So I want you to just look back here to this slide. This is our expression for x in terms of projectile motion. This is our expression for y. A little different for y because remember, these are just your x and y components. And when you have y, you have to deal with gravity. So for the first one, we're just going to use those 2 expressions and plug in the information we have. So 6 is the height. We were told 6 feet. 100 is the initial velocity, and then 45 degrees is the angle. So as we plug those values in, we get our solution, and x equals 5 root 2t. For y, we go ahead and work the problem out, and we get that expression for y. Hopefully I don't have to explain that math. You see it. Remember the root 2 over 2, that's sine and cosine of 45. I know you guys can use your calculators now, so actually, I'm not quite sure what happened there. Hold on. So find the height of the ball. Okay, I switched around. So when time equals 1, let's go back. Sorry, I wish I copied it over. That's a little confusing. So we're trying to find the height of the ball at 1 second, 2 seconds, and 3 seconds. So our height is going to be determined by y. So remember, the distance, like horizontal distance, will be x, and then your height will be y. So we literally just plug a 1 into that equation we derived, and out comes 60.7. When time equals 2, we plug in 2, and when time equals 3, we plug in 3. So if it's thrown from, actually I better go back so you can write that down. I forgot you guys will be taking notes as you watch this. My apologies. So here you go. All these slides you should be able to pull up with all the completed notes as well. So if I ever go too fast and need to explain more, let me know. But there's that. So that a baseball is thrown from same problem, sorry. And then determine how long the ball is in the air. So what we're trying to find, the ball will hit the ground when y equals 0. So we want to see at what point is height 0. So we set y equal to 0. So this is going to give us our time, but then we're still going to have to, or it's going to give us the time, never mind, and that's what we're going to need. So we solve this. This is a quadratic. So we're going to have to plug it in the quadratic formula. It's going to give us 2 times. It's going to give us a negative time and a positive. Remember, we're talking real world, so the negative won't count. So the time that it hits the ground will be approximately 4.5. And then the last 2 parts determine the horizontal distance that it travels total. So we just figured out the time it hits the ground. So that's the time we're going to use. We're going to plug 4.5 in for x. And then we also want to find the maximum height of the ball. So let's do part D first. So we're going to plug in that 4.5 seconds into the x expression, and we get 318.2 feet. Then to find the max y, we just need to find the vertex. So remember that negative b over 2a to find the x coordinate. So we plug that in. We get approximately 2.2. and then we plug 2.2 into y to find our y component, and we're done. Okay, and that is it for lesson 10.7. And again, just let me know if you have any questions, and we will address those in Zoom. So I hope you guys have a great day.